Good afternoon, everyone. My name is Trevor Plint. I'm a fourth-year PhD candidate in the Faculty of Chemical Engineering and Applied Chemistry at the University of Toronto. And I'm going to be speaking a little bit about a combined screening approach for novel materials for organic photovoltaics, or organic electronic devices. So, as we've talked about it today, some of the advantages of OPVs, they have the potential to be light, to be flexible. They also have the advantage from the carbon dioxide point of view of being less energy intensive to produce than, say, silicon cells. But we're still up against this issue that they have not.
I'm just going to turn down the volume. That's fine. Continue.
Thank you. The difficulty that they haven't caught up to silicon and they likely will in our lifetimes, and we're still fighting the cost variable here. So the sort of central crux of the organic electronics development pipeline is that we can't design carbon-based materials with arbitrary electronic properties. So we have to do this the hard way. So we have to deal with material screening. And when we're going through the screening process, well, we're looking for materials that have good charge variability. We're looking for materials that have the right absorption profile for an organic photovoltaic device. And we're also looking for materials with the correct sort of exciton dynamics. But these are all very difficult parameters to measure. So synthetically, what does this mean? Since it's difficult to predict all of these a priori, design them a priori, we start with a motif that we think is promising, and we make variants. And we try those variants and see where we can get with them. So the lab that I work for is carried out by Tim Bender, and we're interested in boron subphthalocyanines, specifically because they are versatile and they are bowl-shaped. They have this sort of curved configuration which disrupts their pi electron stacking, which blue shifts their absorption, and puts it right in the sweet spot underneath the solar irradiance, the heat flux, which is great for us. This is the solution absorption. The solid state is actually considerably broader than this. And we can make all the derivatives of these materials, but since the chemists will always be ahead of the device engineers in terms of cranking out new materials faster than we can optimize them, where do we go from there? So another material that we're interested in are phthalocyanines. They're sort of a planar precursor or predecessor to subphthalocyanines. And for the experiments that I was working on, we started with a group 14 metal phthalocyanine, and we had a whole bunch of derivatives thereof using aluminum as the core material, silicon with either a dichloro or a pentachlorophenoxy. We were also looking at germanium and tin. So these are all materials, these are all atoms that are in the sort of key block of the periodic table, so they're right close to that sort of metal-metalloid line. So those are vicious to us. And it turns out that we can take these derivatives, we can put them in organic photovoltaics for boron subphthalocyanines. But having sort of shown that boron works quite well, we started to get interested in these silicon and germanium materials. We've tried gallium, we've tried indium, and it works as well as we'd like it to, and we're moving towards tin and phosphorus now. And this is kind of where I came into the experiments, is that optimizing an organic photovoltaic device is difficult. It's fundamentally a zero field device. So you're running into problems with morphological characterization, charge transport measurement. You need to know what sort of thicknesses you want, and you need to be able to optimize those. And this is all very time consuming when you can only do this sort of the batch to batch. The device making is not a continuous process. So overall, OPV performance is very sensitive to minor changes in morphology and structure. You run into problems with batch-to-batch variation, and it's difficult to diagnose what's happening purely based on the electrical output. Your KFC changes that can mean any number of various different things. So the question I sought to answer is how can we optimize OPV material selection without actually making any OPVs? So we turn to bilayer OLEDs. So most of my work is actually in OLEDs. And their structure is very similar to a planar heterojunction. Here you've got a hole transporter and an electron transporter. This is what they look like when this is about 1 inch by 1 inch, and the pixel surface is about 1 millimeter by 2 millimeters. And you push electrons in from the top, you push holes in through the bottom using a DC field, and you get light out. There's your pixel light input. So this is great. We can characterize the light output and quantum efficiency of these pixels really precisely, and it's quite easy to do. So, and just to sort of prove what I'm going on about here, the electrical structure for an OLED is you give some energy to an electron on one side, you take away some energy, you crosstalk for a vacancy, a hole on the other side. When the electron reaches the interface, it falls in, they annihilate and they kick off light. So this is very similar to the energetic structure for an OPV, where you're creating this bound exciton, which if it migrates to the interface, a tricky word there, and if it dissociates through some thermal process, your electrons flow in one direction and your holes flow in the other direction. So your bilayer OLEDs and your planar heterojunctions are very similar beasts structurally. So effectively what we're trying to show is that if a material makes a poor bilayer OLED, it's going to probably not be too great as an OPV material. So we went off and made a whole bunch of OLEDs. And this is sort of, I'm only going to show this one plot here because I dread putting graphs into presentations, but this is luminance, so this is the amount of light coming off on a logarithmic scale. Right about here is as bright as your phone camera, your phone, your flashlight, that's about how bright that is, 10 to the 4, and 10 to the 1 you can just about pick up with your eyes. So these chlorogermanium, chlorosilicon, tin phthalocyanine derivatives that we were interested in didn't perform so well. Chlorogermanium had a really early turn-on voltage here. These other two here were lighting up at sort of very high voltages, which is not a good characteristic you want to turn on at as low voltage as you can get. And chloroaluminum showed good performance, and F10 silicon showed even better performance there. So we have this sort of OLED data, and then we went off and made some OPVs, and we saw a similar broad trend. Chloroaluminum had a really good JSC, and F10 silicon had a very good VOC here, so these are both good characteristics. And chlorosilicon is not so good here. Chlorogermanium barely registers as an OPV at all. So by and large, we're seeing some similar trends, even though it's easier to test OLEDs than it is to test OPVs, so we can get a second perspective on the materials as they're coming out of the synthetic side of the lab. We went off and we tested a bunch of chlorosilicon and F10 silicon as OPVs, as both a donor and as an acceptor, so we're able to sort of follow up on these materials when it looks promising. And this F10 does indeed, this F10 silicon PC does indeed show very good performance in OPVs as quite good absorption. So the conclusion that we come to here is that good bilayer OPV materials are also going to be making good OLED materials, and it gives us another perspective on the material. But basically, this is our response to the fact that the synthetic chemists will always sort of have the advantage of the device engineered when it comes to optimizing things. They can always make the material faster than we can get into devices. So until we can design material with arbitrary properties, we're kind of stuck with the screening processes. And the sooner we can hit the economic sweet spot, the sooner we can all get rich. So thank you. I'll be happy to take some questions.
Thank you. Please, questions?
You try to convince me of the fundamental premise here that if it's a good OLED, it's also a good OPV. Because I would say, so typically in OLED, let's say your electron transport layer is also the luminescent layer. You want a large barrier for electrons to get into your hole transport layer, but you want almost no barrier for your holes to get into your electron transport layer. And that's very different from what you want in an OPV. Similarly, you want the delta current in an OPV to be as small as possible, but you want the current to flow very well in an OLED. So can you convince me that
Both good points. I don't know whether I can do that.
I do believe the trend to be so.
Yeah.
And I might be wrong. Maybe we'll talk more about it later.
Sure. Okay. Thank you.
Okay, this is my question that your OLED needs to be one type 1 structure. About level on you understand what I mean?
No, do you have another way to express it?
The energy level of this is type 1.
Right.
This is the type 2.
Straddling the staggers, right? Yeah. Okay. Okay, so you're talking about a dope OLED then, if you want. If you're talking about something that's structured like this, where it's straddled, let's say you have a dope that's inside a host, as opposed to a bilayer one, where you actually want it to be straddled. Does that answer your question?
And then you have error loss in your graph. It's nice, and also often error loss. Can you explain to me how you got this error loss?
For the OLED results?
Yeah.
These guys here?
No. Oh yeah, I think it's good one. The transistor voltage ones.
These guys here? Okay. Okay, so I think the person actually maybe touched on this now. Okay, David said. So effectively what we're looking at for those is our system makes 4 devices at a time, and we can make them in the same configuration. So effectively that's just taking the average across the some sort of OPV pixels on each of those devices. So that's where those error bars come from. This is intra-batch variation as opposed to batch-to-batch. Is that a clear question?
How many different materials do you use?
So for the OLEDs, we went through, animations here. We went through the 6, I think. Okay, here we go. So, yes, we went through, 5 here plus a baseline full transport material.
Okay, and do you have the support from the modeling or calculation of the electronic structure?
To suggest why these would work?
Yeah.
It's a very good question. So there's, you're right, we can do some modeling to determine what the predicted homoluminal predicted material is, say by DSP theory, for example. But there's more to it than just sort of what's predicted. You can predict the homo level very well, the lumo level you run into difficulty. So there's also morphology we take into example. For example, so we had another one here. There was germanium, F10 germanium, which looked like it had all the right characteristics. Germanium, it was a bit of interest industrially in the past, but once you actually make the material, you can synthesize it fine. You can't purify it. It degenerates when you try and use we use a purification technique where we sublime it under vacuum and it comes out in a tube, but it breaks down into a fluorinated version. So you have a fluorinated version. So that's something that you couldn't predict with modeling. So it generally found that trying to make material and then trying to get it into a device